Yeah, so thank you for the introduction. As said, my name is Mikael Brunila, and I recently, as the introduction said, I defended my PhD thesis at McGill a year ago, or October last year. And my discipline was geography, and in this sense, I guess I'm an odd one out at this symposium. But as the introduction said, despite my discipline, I have actually spent a considerable amount of time both working in applied NLP and digging into the history of that field with work published in both EMNLP and NAACL, and recently in eFlux. So today I will focus on the historical and speculative part of my work, drawing a historical parallel between the bit and the embedding, in order to present a theory of how to understand the accumulation of a certain power to abstract, not just in the LLM, but in any system that can be modeled as or in any phenomena that can be modeled as a sequence of events. In this sense, my presentation will brush on really similar topics that were presented yesterday by Leonardo Impet and Fabian Offert, as well as Xiaoshang Li, and many speakers today, including Marvin here. And I'm really curious to see what kind of dialogue the overlaps and contrasts between our work can produce. So now I'm trying to synchronize speaker notes here and slides there, so bear with me as I figure it out. I think, okay. Yes, great. So I will start with 3 claims and 1 proposal. So the first claim is that it's historical and relates the embedding to the bit. So I argue that much like the bit before, the embedding is a foundational unit of information, objectifying various representations of social life as fungible commodities across an increasing range of societal domains. The second claim is also historical and reads as follows. The embedding is produced through an extension of the metaphor of the noisy channel. This extension is only possible through the internalization of the ground of meaning that was externalized in early information theory. Finally, the third claim is more situated in the present, but still draws on an understanding of the bit. Here I suggest that, like the bit, the embedding is produced through the diagram of the noisy channel. Through this diagram, the embedding functions as a new form of capital, cosine capital. So based on these 3 claims, I also make a proposal. Most of critical AI research has focused on the decoder part of the noisy channel. However, at this moment in time, we need to return to the question of ground and contest the accumulation of cosine capital at the encoder level. So just to give you a sense of my outline, I will start by talking about how early information theorists like Ralph Hartley, Warren Weaver, and of course Claude Shannon talked about meaning. I intend to show that meaning functioned as the necessary ground against which the bit could be presented as a purely technical concept. As information theory was picked up by American structural linguistics, meaning was apparently internalized into information. However, a close reading of works from people like Zellig Harris reveals that these attempts ultimately rested on a false confidence. So the question of ground was merely pushed aside but not resolved. So it is from this basis that we can understand the production of embeddings as a semanticization of the noisy channel. Specifically, it is self-supervision as an operationalization of the internalization of meaning that is the key innovation here. I will demonstrate all of this using one of the most simple feed-forward architectures as an example, namely the skipgram implementation of word-to-vec. Next, I will show how the embedding has become a radical tool of flat ontology, with self-supervision proliferating in various contexts. I argue that this proliferation is producing what I call, again, cosine capital, a type of meaning in movement, similar to what Marvin was saying here, akin to Marx's idea of capital as value in movement. Here I'm echoing ideas that, as I said, that were expressed yesterday in several talks. So this gets me to the final and most speculative section, where I return to the noisy channel to propose that we need to imagine and strengthen paradigms of private AI that provide an alternative encoder politics that doesn't contribute to the circulation of cosine capital without turning towards a pure or naive refusal for that sake. So, information theory is today one of the fundamental engines driving LLM development and operation. However, while it is information, usually through cross-entropy loss, that function as the criteria for training these models, early information theorists were quite adamant that semantics had no place within information theory. In this section, I will give a refresher on the bit and review observations about the relationship between meaning and information among some early pioneers in information theory and structural linguistics. So, let's revisit this image, Claude Shannon's noisy channel, which I imagine many of you have probably spent considerable time with at some point. In it, communication becomes a system of encoding and decoding messages from signals. Bits encode words, words encode intentions, and so on. The noisy channel starts with an information source that produces a message, for instance, words on a screen. These words are then encoded as bits and transmitted as a signal over some physical channel, like fiber optic cables, to a receiver device. This device then decodes the received bits into the original message. In this depiction, as Michael already has noted, communication acts as a conduit. Words are just vehicles for unambiguous semantics. So let's hone in on that part where words are turned into bits. As we know, bits represent data as binary yes or no choices, 0 or 1. When we take the average number of bits required to encode a set of symbols, we get what is known as information entropy. To take a very simple example, imagine a language with 4 symbols, A, B, C, and D. Each of these is equally probable, so they each have the probability of 0.25. To represent them, we need on average 2 questions. First, we could ask, is it A or B? If the answer is yes, we can ask, is it A? If the answer to this question is yes, we know it is A. If the answer is no, we know it is B. And then we can repeat this procedure for C and D. So you can see this logic at work in the table to the right. Another way to write this table is through the equation for information entropy, which you can see on the left side of the slide. Here we see another variant of our 4-letter language, this time with different probabilities for different letters. In this upper table, we assume that all letters are equally probable and encode them with 2 bits. This gives us an entropy of 2, again, as it gave before. In the lower table, we use the actual probabilities of the letters and get an entropy of 1.75. In this case, this is the most efficient encoding. In other words, for the bit, the noisy channel diagram promotes a norm of efficiency where symbols should be encoded corresponding to their relative frequency. This idea is, of course, much older than information theory, as the allocation of symbols in Morse code highlights. All that I've presented so far is basically adapted from Shannon's foundational 1948 papers on information theory. In these same papers, Shannon introduced the notion of relative entropy, which is calculated by comparing the maximum entropy, the second table in the previous slide, to some presumably other code, the first one and the second one. Through the work of Solomon Kalbach and Richard Leibler and later Irving Good, this metric became what we today know as cross-entropy loss, the most common loss function for optimizing LLMs. Nevertheless, as I already said, and as many of you surely know, Shannon was adamant that semantics had no role to play in information theory. In fact, Shannon's sentiment was continuous with the prevalent ideas regarding information. It was to be a technical concept purged from semantics and psychological factors. In work that Shannon was building on, Ralph Hartley from Bell Labs had put meaning in the position of a decision that was external to the system of information. In one of several very instructive quotes from one of his most influential papers, he wrote, "There must be a group of physical symbols, such as words, dots, and dashes, or the like, which by general agreement convey certain meanings to the parties communicating. Note that meaning here is external to the system, something that is reached through general agreement." In the philosophy of information, this problem that Hartley and Shannon were grappling with later came to be known as the symbol grounding problem. Somehow, we must enclose the meanings of symbols for them to be disclosed within a system. Let's return to the example of Morse code. So borrowing terminology from anthropologist Paul Kockelman, we could say that deciding that E will be encoded by 1 dot is an act of enclosure, which makes it possible to disclose E through revealing the dot. While philosophers of information don't typically think of the question like this, symbol grounding can be extended. For land to be disclosed with a value, it must first be enclosed through all kinds of violence, law, socialization, etc. So this gets us to another claim. Resolutions to the question of the ground mark steps in the evolution of the relationship between linguistic meaning and information. Against Shannon's purely technical concept of information, Warren Weaver took a much more semantically oriented approach. In his famous text on machine translation, he suggested that the meaning of words could be determined by looking at their context. If we understand words as form, then meaning was derivable from the interplay of these forms, just like information was derivable from the form of bits. However, Weaver still restricted meaning to the task of word disambiguation. It's only Zellig Harris that fully internalized meaning into form, blurring in turn the boundaries between information and meaning irrevocably. For Harris, the lexical meaning of a word was always defined by its set, i.e. words that it appeared with, without, in contrast to someone like Weaver, a reference to any external thesaurus or the like. So today, Harris's ideas can be illustrated with the formation of training samples for a masked language model. As many of you surely know, here a sliding window is moved over all of the data with the goal of predicting the orange context words from the green center words or vice versa. Through learning this prediction task, a neural net forms the weights, i.e. the embeddings, that then come to represent lexical semantics. This gets us to another claim. It seems to me that it is this very internalization of the ground that has made it possible to flatten the world into tokens to be modeled by self-supervised learning. However, despite the best efforts of some of these thinkers and tinkerers to either ignore or internalize the ground, the outside persists. For example, in Harris's case, he had to somehow determine what the basic units of analysis in his theory were, which in his case were morphemes, a morphological unit of language that cannot be divided. In order to identify these morphemes, Harris devised something he called a pair test, where native speaker recognized boundaries between morphemes. It was through these innate abilities of people speaking a language that the boundaries of words, both written and spoken, could be determined. The right side of this slide shows what kind of tricks the other thinkers have referenced in order to resolve the symbol grounding problem, but I'm not going to go into details on them. So let's keep this insistence of the outside ground in mind as we now move from bits to embeddings. As I said earlier, embeddings appear to me as the product of the semanticization of the noisy channel. Let's see why that is through inspecting a very simple neural network, the skipgram version of word2vec. So to reiterate what has been covered many, many times during the past 2 days, embeddings are representations of words in vector space. The dimensions of these vectors have no obvious human interpretation, making them a sort of machine semiotics. In this figure, similar words have similar colors in similar positions, but neither the colors themselves nor the number of colors mean anything. And as we also have seen many times during the symposium, similar words have similar embeddings. So this similarity, sorry? Oh, someone just coughing. Okay. The similarity is typically measured using the cosine similarity between the embeddings. So we know what an efficient bit looks like, but what makes an embedding efficient? Let's approach the question through an example that would also, and perhaps more importantly, demonstrate how language models function as noisy channels. So this is a very simple neural network based on an implementation of skipgram in NumPy. It shows one pass through a language model where we try to predict context words using a target word. Here, our target word is the word communication, and we're hoping to predict the words engineering and problem. So we start by encoding the input message with a vector that just tells us that our input message is the word communication. Next, we encode this word using an encoder or an embedding matrix for the target word. This encoder multiplied by the input vector gives us our signal. Now we multiply the signal, or the hidden layer, with a decoder matrix which embeds the context words. This gives us our predicted output context as message. We use a so-called softmax transformation to turn the output into probabilities and then pick the top 2 probabilities. In this instance, when I ran this through Python, we got the wrong prediction. However, if we were to train this net for a few epochs, it will give us good outputs. In this way, this model provides a simple illustration of how the neural approach to language modeling leans on the noisy channel metaphor. There is an information source that provides a target word, which is the message that is encoded into a signal using a transmitter. The signal is then decoded using the context embeddings of the receiver to provide an output message, the context words. Oops, sorry, I was one slide ahead in my notes. Everything I said, but for this slide. Okay, so what the efficient embedding does is that it serves the purpose of next token prediction. It is supposed to give us the type of output in this figure. To get these predictions, we need to find the encoder and decoder that provides the correct output prediction. In this sense, with the embedding, we have gone from assigning bits to learning weights of neural networks. This is also why some AI researchers have noted that LLMs function as compression, as the final speakers yesterday also pointed out. Let's also note in passing that the transformer architecture is divided explicitly into an encoder and decoder part. Now, as many have already proposed during the symposium, language modeling and embedding seem like a novel and more intensive form of data extraction. Among the tech giants, the value of embeddings has been duly noted. Already in 2017, Meta published a preprint of the paper you see here, which provided a general-purpose approach for embedding various objects of interest on platforms like Facebook and Instagram. The title of the paper, Embed All the Things, has turned out to be prophetic, to say the least. So I propose that the noisy channel acts as a sort of diagram that determines what can be seen and known. As such, this diagram relies on the technique of self-supervision. While supervised learning is measured against predefined labels, for instance, ham or spam for emails, self-supervision uses context to predict the words themselves. Right now, self-supervision is proliferating, again, something that was noted yesterday. Any sequential activity can be modeled through self-supervision and ergo also represented as embeddings. In 2017, data scientists at Tinder showed how users of the app could be embedded using swipes as sequential data. This can be seen in the top figure. The bottom figure, again, shows a similar logic for recommendations on Spotify. Here, a research paper by the data science team at Airbnb from 2019 demonstrates how Airbnb listings can be represented through comparing clicks in a browser session. So rather than represented through their qualities, size, location, etc., these listings are similar because they appear in similar browser sessions. They're not represented by their attributes, but the embeddings result from a particular behavioral pattern. So it is the accumulation of these embeddings that I call Cosine capital. For Marx, capital was not something you held, but value in motion. The capitalist starts with money, invested in a commodity with the purpose of selling that commodity for more money or money prime. Similarly, cosine capital is meaning in motion. We can conceptualize this motion in a number of ways. On a pragmatic level, a user of ChatGPT prompts the embeddings of the model. These prompts and interactions with the model produce content which can be used to train more models to produce more embeddings or embeddings prime. This is also a process of form turning into meaning and back into form. It is likewise a process of encoding, decoding, and encoding prime, and furthermore, a process of enclosure, disclosure, and enclosure prime. As this circulation intensifies, the new masters of meaning will be those who control the best embeddings. Here I want to stop for a minute and contrast cosine capital with what Marian Fourcade and Kieran Healy have called eigencapital. The important distinction here is that eigencapital always serves ranking and ordering, which is not true for cosine capital. Cosine capital is generative. It produces a regime of signification that is not good or bad, but rather hegemonic. It produces a world, or maybe rather a normalized code of the frequent, the typical, and the least controversial, as Tobias Matzner said earlier, commenting on the transformer LLM. So why introduce a concept like cosine capital? What I hope to show in this last section is how understanding LLMs in terms of the noisy channel and the accumulation and circulation of embeddings can open up a horizon for thinking about political interventions in AI. One way to think about this is to actually look at Shannon's noisy channel and consider where political intervention could occur. From this vantage point, we can imagine a sort of decoder politics which focuses on mitigation, deliberation, and interpretation. It focuses on critique, in other words. Much of my own research is in this domain. On the other hand, we could imagine an encoder politics. Here we could try to define the parameters of disclosure, drawing the enclosure instead of being drawn into it, proliferating and taking collective control over the embedding spaces of our lives. While I rely on a Marxist framework, I think it's fair to say that it's habitual of Marxists to decry abstraction per se. However, at this point, I think the greatest challenge we're facing is not so much about abstraction, but the way in which abstraction and erasure of ground is combined with centralization to produce both homogenization and massive power asymmetries. The question then would be about how to encode and abstract differently, avoiding the centralized gaze of AI as platform. How could we fragment AI and destitute its centralized gazes? I will point to 3 different technical innovations that I have outlined in greater detail in a recent eFlux article. Firstly, small language models offer the possibility of running models locally on a device. In this situation, there's no need to contact a centralized server, such as those of OpenAI or Google. The encoding involved with fine-tuning your own model is removed from the client-server relationship that characterizes cloud platforms today, including LLMs. A second innovation is federated learning, where model parameters are shared instead of data. Now encoding happens among a cluster of trusted peers, again removing it from the client-server relationship. Finally, an interesting emerging technology is private information retrieval, or PIR. In a nutshell, PIR would allow us to query a server for a calculation without revealing what we are asking for to the server or letting the server itself know what it will answer us. If the example was 5 + 4, it would proceed like this. We send the query, it is encrypted. The server performs the calculation without knowing exactly what it is doing. The server returns the result without knowing what it returns. We decrypt the result and get our sum. Of course, there are important obstacles to each of these approaches. Small models are less convenient than large models, and we know people love convenience. Homomorphic encryption is slow and computationally expensive and does not break with centralization per se. Federated learning is no panacea either. It can be used to justify centralization while offering a false impression of real privacy. And finally, all frontier research is controlled by large private companies, or in the case of China, government actors. So what can we conclude from all of this? Perhaps that the symbol grounding problem reimposes the question of ethics. Any system rests on some ethical or political ground, i.e. the moment of encoding and enclosure. I believe this is where interventions must happen for AI to deliver anything but a dystopian future. Thank you.